and welcome to the first pre-recorded class of business calculus. And today we're going to look at the derivative. And so far we've been looking at slope, and when we look at the derivative, we realize, well, what we will realize is that basically it's the same thing as the slope. The derivative, technically, measures the rate of change. So if you have an equation, and for example, how fast a car is going, what is the rate of change? How fast are you going over time? A rate is always measured at a particular point, and it is oftentimes used in business to measure something like the sales rate. Not the actual amount of sales, but the rate that sales are happening at. We will see a few examples of this shortly. A few semesters ago, I took a survey of students and asked them how much sleep they got at certain points in the semester. And of course, as you can see on the screen, the week before the semester starts, students said they got about 9.3 hours of sleep on average overnight. And in the first week of the semester, of course, that dropped significantly. And then, of course, the ninth week it went down even more. The ninth week was the week before break, which would be referred to as midterm week, where there's a lot of exams and papers due. And then, of course, the 10th week was break, and naturally, the amount of sleep went up. The students are recouping and just having a chance to get more rest, so they do. And then we jump straight to the 15th week, the week before finals week, where a lot of exams are happening and so on. And we find that that's the most stressful week of the semester for many students, and it's when they get the least amount of sleep. Now, if we're looking at the sleep, we can look at it as time, but the rate would be comparing two of these things together. So when we're looking at the hours of sleep, this is simply a graph of that. The rate is going to be the line that's between those, like for example, between week 0 and week 0 here and week 1. The rate is going to be this line, how much change is happening. So again, a derivative will measure the rate of change, and we also know that the slope between any 2 points is the same thing. So we begin to discover, okay, the concept is that the slope and the derivative are the same thing. In calculus, we move beyond slope and finding the slope at a specific point, but it's a good starting point. Now, if we wanted to measure the rate of sleep, what we can do is go back to slope and say the change in y over the change in x. And of course, we can, in this case, we have 2 points, an x1 and a y1, and an x2 and a y sub 2, and we can use that. So, just to make it clear, I've added here a line looking at the different weeks. Well, when we're graphing this, we realize our x at the first one is when x is equal to 1. At the second one was when x is equal to 2, and so on for the 5 different points. We're not actually measuring the amount of change every week. It's simply measuring the rate, the changes between these 5 specific weeks. For example, if we go back here, when we look at this, we know that from week 1 to week 9, that it goes down by 0.9. Week 9 is 6.5 hours of sleep, and week 1 was 7.4. If we subtract that, we get 0.9. So that's almost an hour less of sleep from the first week to the 9th week. That doesn't mean that it's almost an hour every week until we get there. It's comparing just week 1 and week 9. So, giving it the x values just to make it clear, when we do the slope, we would take the slope from week 0 to week 1, put it into the formula, and y sub 2 minus y sub 1 over x sub 2 minus x sub 1, and we get minus 1.9, or almost 2 hours, 1.9 hours less of sleep from week 0 to week 1. If we go to compare week 1 and week 9, then we use, again, from the prior page, 7.4 minus 6.5, and it's the third point minus the second point of the x values, or the x coordinates. So, again, 9/10 of an hour less sleep, or about 54 minutes less sleep. And if we do for the rest of the time, we can look at it and say, oh, this is how much change is happening. From week 9 to 10, 3 more hours. It's positive. So students get an extra 3 hours of sleep. And then from that week to the most hectic time of the week right before final exams, the reduction is by 3.4 hours. We've been looking at the slope, but that's also a rate of change. I've used that many times. So we can actually think of this as the derivative. It is indeed a rate of change. The derivative measures rates of change. And so again, the conclusion is that the derivative is the same thing as the slope. Now, in working with a business problem, a manufacturer finds that the total cost of producing X units is 2X plus 1,000 liters. If we were to graph this, we would simply say that the cost function, this C of X, is equal to 2X plus 1,000. So a graph of this appears here on the screen. And this is what we're used to seeing in math, but what does this mean in business? If we try to make a link from math to business, what's the economic significance of the y-intercept? That's worded rather difficult, right? Well, I know, the wording is such, it's not what I consider to be ideal, it's how the book is going to put it. So when you're looking at the homework, and they talk about this kind of thing, what's the economic significance, now we'll have an idea what it means. What is the y-intercept? And what does that mean in terms of business? What does this mean to this particular company? Well, when we look at it here, we realize that here the y-intercept is at the y equals 1,000. And of course, going back to our formula up here, the cost function, if we remember the y equals mx plus b, when we use excuse me, when we use this form, y equals to the slope 2x, 2 times x, plus the y-intercept. So again, we know that this is going to cross right here. Well, what is the 1,000? In this case, it's 1,000 liters. What does it mean? Well, the 1,000 liters are the fixed cost. If you remember from your introduction to business class, you should have heard terms like fixed cost and overhead. What are they? Well, if you dig around your memory a little bit, hopefully you remember. These are costs that are ongoing. They happen all of the time, but it doesn't actually deal with the product itself. For example, insurance, you have to pay insurance if you're producing things. Maybe you're paying rent or a mortgage. It doesn't directly go into the cost of whatever it is you're producing, but it is an indirect cost that affects what you're going to set your price at to sell a product. Electric, heat, the wages that you pay for people, these are overhead. So that means even if they don't produce anything, when here an X is 0, they still have cost of 1,000 liters. So they have to include in, when they're going to sell this, they have to include enough to cover the cost of the material itself plus these overhead costs. Now, what's the economic significance of the slope, or as we're saying, it's also the derivative? Well, the slope, or the derivative, is this 2x. The slope is 2. Well, what is that? Well, the slope, in this case, it's equal to 2, and that means it costs 2 liters to make 1 unit. Whatever it is we're producing, it's not terribly expensive, but 1 unit will cost us 2 liters to make. And since it's straight line, we know that even if we make 5 units, the cost at 5 units is still, the marginal, excuse me, the cost to produce each unit is still 2 liters. If we continue the graph off the page here to where x is equal to 10, well, the cost still to make 1 more unit is still 2 liters. And this is the marginal cost. Hopefully you remember this term from your Intro to Business class. But it's the change in total costs that occur from producing just 1 more unit. It doesn't include the overhead cost, the insurance, the rent, the wages, electricity, that kind of thing. It simply is how much it costs to produce 1 more unit. And since this is a straight line, it's the same everywhere. When we produce 5 units, it's going to cost us 2 liters, two more liters to produce the next unit. So that's the economic significance of the slope in this case. It's the marginal cost. So now we begin to discover a business application. When we're working with slope and we're working with the derivative, it is actually equal to the marginal cost. And this is something you want to remember throughout the course, because we will use this very frequently, all of the time. Now, working with depreciation. Here's an example. Trusting you remember what depreciation is from your intro to business class. If you purchased a printing press for 500,000 euros and you decide to depreciate it at 50,000 euros per year. With depreciation, that's an amount that you expense every year, or sometimes people do it by month or by quarter, different businesses. But it's a matter of you do depreciation. You set aside money so that when the machinery is worn out, you can purchase another one to replace it. Now, what would the formula be for the value of the press? We purchased a printing press for 500,000 euros, and we depreciate it at a cost of 50,000 euros per year. So if we look at this, we realize, well, the cost is going to start at 500,000 euros. And then each year, the value of it's going to depreciate down 50,000 euros. And we're setting aside 50,000 euros to replace the machine. So at the end of 10 years, we can buy a new machine. Well, what would that kind of formula be? Well, just the way I described it. The value of the press right now, when you first buy it, is 50,000. And you're going to subtract 50,000 for each year. So we have our function, f of x would be the value of the printing press. And it starts out saying, well, it's going to be 500,000. And each year, we're going to subtract 50,000. So x represents the number of years, and we multiply that by the 50,000 per year. So at the end of the second year, x is equal to 2. We're going to take 500,000 and subtract 50,000 times 2, or 100,000. But the value is going to be 400,000. So this is the kind of logic that you step through for finding the value of it. And again, the depreciation amount that we're going to do is going to be 50,000. That is simply just the 50,000 times x. Well, I shouldn't say times x, because it's every year. Set aside 50,000 every year. And if we look at this, we realize, okay, well, let's go back and let's ask our questions. What's the importance of the y-intercept when we're working with this? Well, if we were going to graph this, we can look at it and say, we can do this. We have the formula in the form of y equals mx plus b. Now, in this case, it's a little bit backwards. If it's mx, the slope's going to be m is going to be minus 50,000 x plus 500,000. So the y-intercept, we know that's going to be out here at 500,000. And now the slope is minus 50,000. So if we're setting this up, and this is at 250,000, k represents 1,000 kind of thing here, so you're aware of what's happening. And each year, it's going to come down 50,000. So each of these lines is 50,000. So at the end of the first year, the value is going to be there. The end of the second year, the third year, and we end up making this line is going to depreciate, something like that. We'll make a better, more accurate graph of this shortly. Now, if we're looking at this, what is the importance of the y-intercept? Well, hopefully this is relatively clear, that the 500,000 is simply the original purchase price. And here's a little bit better drawn graph than what I did of the same thing. And what's the importance of the slope or the derivative? Well, again, we said that's going to end up being the amount that we depreciate, or it's also the decreasing value of the press each year. It's going to go down 50,000 euros per year. When we're working with straight line depreciation, we also can say that's the depreciation rate. We're going to reduce it at a rate of 50,000. Since it's a rate, we know that it's excuse me. Since it's a rate, we know that that rate and depreciation, or excuse me, the derivative are the same thing. So it's also the derivative, it's the slope. Now, going back to the point-slope form of an equation, if we wanted to create a function, which is a formula, it's easy to do if we know the slope and the y-intercept. We just did that in the last problem. But what if we only know the slope and a point on the line that is not the y-intercept? So, for example, if we knew that the slope was 3, and we had a point at 2, 5, well, could we create a formula for this? Well, we know that m, the slope, is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Well, maybe we could do just a little bit of algebra to this. If we were going to try and make this a little bit nicer and get rid of the fraction over here, we could multiply both sides by x sub 2 minus x sub 1. Over here, they would cancel each other out, and we'd end up with m times x sub 2 minus x sub 1 equals y sub 2 minus y sub 1. Now, when we're used to working with formulas, we're used to seeing the y come first. So let's just look at it in that respect. Now, if we're going to use this, we're going to end up with a y sub 2 and also a y sub 1. Well, you know, we have a point, right? Over here, the 0.25. And when we look at it, we're as, well, couldn't I take this 5 and put it in for one of these numbers? Well, yes, I could. And I have an x, and could I put that in for one of those x's? Well, yes, I could. If I did that, then I'd be left with just a y and an x, which is all I need for a formula or for a function. So we can do that. And to make it a little bit easier, what we can do is say that the point-slope form of the equation is this. It's going to be y, and this is the y that we'll leave there, we won't ever change it, minus y sub 1, the point that we have. We only have one point. Equals the slope times x minus x sub 1. So if we're going to work with this, we're going to simply make the equation and say, again, the y, the first one doesn't change, minus, now I come over here and say, the y value here is 5. So I'm going to put 5 in for y sub 1. And that equals the slope. The slope is 3. So that's 3 times x, again, the first x and the y we're not going to change, we'll leave them there, minus x sub 1. Well, that's the x coordinate of the point that we have, which is 2. So it becomes x minus 2. Now, we're used to seeing y equals something, so let's do that. In order to do that, we have to do the algebra and say that this is 3x minus 6. When we add 5 to both sides, we get y is equal to 3x, oops, not plus 1, minus 1. So now, we found our equation. Is this an acceptable formula? Yes, of course. 1y, and says y is equal to something in terms of x. So this would be the formula, the function that we're trying to find in this case. Now, when we're working with slope, there's a few things that are helpful, and especially when we're working with some of these lines that in homework, if we remember some of these things, it just makes our work easier. One of the things is that lines that have the same slope are parallel. The distinct means that they're two separate lines. So if you had one line, and for example, let's say it was going like this, another line that's not that same line, it's distinctly separate, it has the same slope, we realize, oh, well, yeah, it has to go up at the same rate, that they would have to be parallel. So it's a simple thing to remember, so that if two lines are parallel, they will have the same slope. The other thing is that if you have two lines that are perpendicular, then, let me review here just to make sure everyone remembers perpendicular. If you have one line going this way, and another line going this way, they are perpendicular if it's 90 degrees, a 90-degree angle between these two lines. And so we look at it and say, if we have this kind of situation, we have perpendicular lines, then if you multiply the slopes of these two lines, green lines that I've drawn, the result will always be -1. Now, that probably looks a little bit better written like this. The slope of the second line is the negative reciprocal of the first line. I know it sounds like a lot of math jargon, but it's not too difficult. If m sub 1 is the slope of the first line, and the slope of the first line is 3/2, the negative reciprocal means I'm going to take this slope, negative means I'm going to put a negative sign there. The slope of the second line will then be negative, and the reciprocal means you take the 3/2 and you flip it over, it becomes 2/3. So if you know the slope of your first line, and you know that the second line is perpendicular to the first line, then the slope is going to be the negative reciprocal, or -2/3. And as we said at first, if you multiply the slopes of two perpendicular lines together, the 3/2 times the -2/3 equals -1. Now, this is the mathematical way of saying it, but in realistically, when you're using it, this is what you're interested in. The homework will tell you the slope of one line, say the second line is perpendicular, and you have to remember that it's the negative reciprocal. Now, so far when we've been looking at the slope or the derivative, we've seen the slope to be how much less sleep you get before exam weeks. Well, it's not the most cheery thing, but it's a rate, right? Now, we've seen slope as how steep a line is. The derivative is going to be basically the same thing, except we define it more narrowly and say how steep a line is at a particular point. We've also indicated that the slope or the derivative is also the marginal cost, and in business we'll use this frequently. And we've also defined it as the depreciation rate. And if we look at this, of course, the pattern that we find is the one we introduced at the beginning, that the slope is the rate of change, and of course the derivative is also the rate of change. The two things are the same, they're synonymous. So again, when we're looking at a rate, it's how fast things change. So the rate of change, how fast does something change? Now an example in using business situations. In May of 2003, Canada banned exports of beef due to mad cow disease. And on September 1st of that year, the ban was lifted. They could now sell beef and export beef again. And the beef exports steadily increased by 42.5 million Canadian dollars each month until the end of December, when they reached normal levels. Now, if we look at September as being the first month, and specifically September 30th being the end of the first month of exports, express the value of the exports in terms of time. Well, sounds a little bit scary at first, but if you realize what I'm looking at here is trying to use the information that I have and put it into a mathematical formula. So we want to find the value of the exports in terms of time for the first month. What were the exports at the end of the first month? Well, on September 1st, they started, right? And the exports steadily increased by 42.5 million Canadian dollars each month. Oh, well, on September 1st, if they lifted the ban, by the end of that month, at the end of the first month, the amount of exports must have been 42.5 million Canadian dollars. If it went up that much each month, it started at 0, and it went up to 42.5 at the end of the first month. So we know we need that. But isn't that a rate? I say yes it is, because it will go up again the next month by 42.5. Think of it this way: at the end of September, they had exports of 42.5 million. The total was 42.5, and if we looked at the end of the next month, well then again they went up 42.5 million, but they were at 42.5. So that means that the total exports for both months would be 42.5 plus 42.5. Oh, well, that's the same thing as 42.5 times 2, right? And we're looking at the second month. So now we've begun to discover possibly what the formula could be. One way of doing this is to go and say, well, let's use our point and our slope. If we look at this, we can say we have a point here, and at the end of the first month, we had 42.5 million Canadian dollars. Time is our x, and the Canadian dollars is our y. So if we wanted to graph this, we would say, well, we have a graph over here. We know at the end of the first month, it was up here at 42.5, and before this, it was 0. I missed the origin there a little bit, but you have the idea. Now, the slope, we could look at this two ways and say, the slope, our m, that's going to be, well, if we come back over to our graph over here, here it's at 42.5, and it was at 0. So the change in y, this direction, is 42.5, and the change in x is simply 1. So the slope is going to be 42.5. Now, when we're doing this, we can also look at the problem and say, oh, they actually told us what the slope was in the problem, because it says that exports increased by 42.5 million CAD each month. That's a rate over time. That's the slope, 42.5. So now, using this, we can come in and say, we use the point slope form, y minus, we use the 42.5, the y coordinate of the point that we have, equals our slope, which is 42.5, times x minus our x coordinate of 1. So again, when we're looking at this, the 42.5 comes from the y value, and the 1 comes from the x value here. So now we can, oops, you erased a little bit too much there. Maybe I'll leave the rest of it there. Now we just simply do the algebra. Y is equal to minus 42.5 equals 42.5x minus, so we take 42.5 times minus 1, 42.5. If we add the 42.5 to both sides, we get 0. So we get y is equal to 42.5x. Now, this is the formula that we're looking for. Now, this worked well using the point slope form, but had we used the slope intercept form, it may have been even easier. The slope intercept, of course, is y equals mx plus b. And if we look at the problem, we realize that, the y-intercept, we even drew it over here, is down here at 0. But we realize 0 represents before the exports were lifted. Well, they didn't have any exports, so the value has to be 0. So the y-intercept has to be 0 here. And if that's the case, y equals our slope, we had said, we figured that out, is 42.5x plus 0. Well, then simply, we didn't have to write that, but since we did, we'll rewrite it here and say y equals 42.5x. Either way, it works. And if you saw it the second way, it's probably a little bit faster and just a little bit less work. But either way is correct, and you could use either of these in these problems, and as you can see, you get the same answer. Now, continuing with the problem, how much beef export in Canadian dollars occurred when Canada returned to normal levels. Well, this is kind of interesting, right? How do we know what normal levels are? Well, they give us a clue to that. They say that up here in the problem, that exports steadily increased by 42.5 million CAD each month until the end of December. So if that was the end of December, and we started exports, the first month is at the end of September. The end of September is the first month, October would be the second month, November would be the third month, December would be the fourth month. Now we have our formula from before. What's now on the screen is y is equal to 42.5x, and x is going to be 4 months later. So we use an x of 4 when we're doing this. So now, using our function notation, we'd say f of x is equal to 42.5x. What we want to do is an f of 4. And of course, we plug in 4 for x, and we get 42.5 times 4, which equals 170 million CAD. So that's the beef export, the normal level that they came back to by the end of the year in 2003. Now, back to this curve about the hours of sleep again. I said curve, that's a little bit strange because it looks more like jagged lines. Well, if it's not a straight line everywhere, we can, in math, describe it as a curve. And realistically, when we look at this, we realize that from the first week to week 9, it's not that he had a steady decrease from the first week to the 9th week, and it's the same all the time. Even in week 0, that we started before the semester, that it wasn't that we simply each night reduced by the same amount of sleep until we got to the end of the first week. More than likely, it dropped off significantly once the homework started, and then just continued until you got to that point. Well, if that's the case, things would look a little bit different. It could potentially have looked a little bit more like this, and then maybe again right before, and then jumped probably up, and then started a slow decline, and then got really bad as it got into the final. Well, if we wanted to find the slope or the derivative of the curve at these points, wow, now it's a little bit more difficult. We look at it and say, it was a nice straight line before, so we could just take the slope. But if I wanted to find the derivative or the slope here, it's going to be drastically different than it is here. And of course, it's drastically different than it is here. It's not going to be, again, the average between these 2 points. It's the slope, the line that's tangent to this, is going to be more like this. So we realize that in a curve, it can change significantly in a short amount of time. And at each point, the slope can be different. It's not a straight line anymore. Well, how could we do that? Well, maybe we can do this. In fact, even if we use something that's very familiar to you. I'm at least hoping it's familiar to you. In high school, when you had your geometry class, if you had a circle, and your teacher probably talked about a tangent line. So, what was a tangent line? I have to remember this. Well, again, a tangent line was a line that touched the circle at one point and only one point. And if we put the radius of the circle here, the tangent line was also perpendicular to the radius at that point. And it only touched the circle at one and only one point. Now, if I wanted to find the slope of this circle at that point, specifically at this one point here, if it's the tangent line, if the slope is the tangent line at this point of the curve, I could take the slope of the red line and find out what it is. Well, how do we do that? I say, that still looks difficult. But would this make it easier to do? Oh yeah, that would be a lot easier. We could come out here and say, well, let's look at the line here. We realize, excuse me, again, using this method, finding the slope, we can try and find a point where touches the x between an x and a y on the axis evenly. Okay, this point is pretty close here, and now it's going to be a little bit further off, and to find a point pretty far up here somewhere probably. But we could, if we extended this red line, find the slope of this tangent line, which would be the slope of that point of the circle, which is also the derivative of that point on that circle. So that's what we need to do. If we can draw a tangent line to the point where we're trying to find the derivative or find the slope on a curve, then we will find the slope or the derivative at that point. Now, here are three different lines, and at each of these there's a point P where we want to find the derivative or the slope at that particular point. Now, the little boxes then are taking that portion of the graph and enlarging it. So now what we want to do at point P in the second row is draw the tangent line to that point. It touches the curve at that one point and only that one point. So what we can do, as you can see here, in the third row, if we have, again, the curve, a point P, the tangent line, in the first case here, the tangent line touches just at this point, and it's all underneath of the curve. In the second one, the tangent line touches just point P and nothing else, and we notice that the tangent line is above the curve at every point. So usually, or I should say not usually, often, this will be the case, the tangent line will either be below or above the curve, but there will be some times where the tangent line actually goes through the curve. That it starts out here in the bottom, and to be able to go through that one point and only that one point, then it will go, once it goes through that point, it'll be on the top side of the curve. Now hopefully that makes sense from what's up here, because here it's starting to come down and it comes over, and then it starts to bend the other way. So in order to get the tangent at this point, it has to go through, because it can't be on either side of it. So now, if we can find the tangent line and put it on a Euclidean graph, a regular graph paper, then we can actually find the slope or the derivative by finding the slope of the tangent line. Now, to practice that a little bit, if we look at this particular graph, very familiar parabola, y equals x squared. Now, at x is equal to 1, what's the slope going to be? Well, if we use the method that we did before, we know it touches right here at this point, and we can follow this up, and you can see it's not quite 100% and not quite 100%. The graphing utility of PowerPoint's not the best. I can't get it quite perfect there, but you can see it's at the same here as it is here. So we look at the change in y over the change in x. The slope, which is now the derivative, is going to be, well, changes 2 units from here down to here, and the y is 1, 2, and in the x's, it's a change of 1. So the slope will be 2. If we go to x is equal to 2 at this point here, we follow this line and realize, up here, this is clear, it comes right there. The graphing utility worked well this time. And the change is from here down to here. So it's 1, 2, 3, 4, the change in y over the change in x, again from here to here, is just 1. And of course it's positive, it's going up. And at x is equal to 3, we do the same kind of thing. It's going to be here, and we'll follow it down and realize that here it crosses. The change in y is 1, 2, 3, 4, 5, 6. 6, and the change in x's is from here to here, the change in y. So the slope is going to be 6. Now, if we go on the other side of the parabola and do the same kind of thing, at x is equal to -1, the slope of the tangent line, that crosses closely here, and again, it's very close here. So the change in y is 2 over the change in x of 1. So the slope is going to be -2 because the slope is going down as you read it from left to right. so the slope is minus 2. If we do that for the other points, at x is equal to minus 2 and minus 3, hopefully we understand that we will get the same values except negative. Since the parabola is reflexive, the slope as it goes up will also be the same as the slope as it's going down, but negative because it's going down. So we look at this and say, wow, we can do this and find the slope at any particular point. We can find the derivative at any particular point by taking the tangent line at that point and finding the slope of that line. So again, slope and the derivative are the same thing. Now, if we wanted to do this for any point on this curve, we can do this and draw the tangent line and do it every time. But we've noticed a pattern, hopefully, when we looked at this. When x was equal to 1, the slope was 2. When x was 2, the slope was 4. And when x was 3, the slope was 6. When x was minus 1, the slope was minus 2. When x was minus 2, the slope was minus 4. And x is equal to minus 3, the slope is minus 6. So what's the relationship between x and the slope? Well, we realize that if we double or take the x value and multiply it by 2, we get the slope. So we would express that mathematically as 2x. We take 2 times the x value where we're taking the slope, and we will find the slope. If we did it at x is equal to minus 4, then it would be 2 times minus 4, the slope would be minus 8. And the same at positive 5, for example, with the slope would be 10 because our x value would be 5. So hopefully this makes a little bit of sense. There are some times we can find a pattern to this, and once we see the pattern, then we can calculate the slope at any other point on this curve very easily and very quickly. So what we're really saying is that the derivative is the slope of a curve at a particular point. One way of calculating the derivative is to find the slope of the tangent line at a specific point of the curve. And in using that in a business situation, one of your production warehouses uses about 400 cubic meters of DUOS, natural gas, per day. Below is a graph of how much DUOS you have in tanks over 2 days. So at the beginning of March 5th to the beginning of March 6th to the end of March 6th, again 12 a.m. to 12 noon, 12 midnight, 12 noon, 12 midnight, excuse me, on the X. So you start here and realize, okay, the usage is varying throughout the day. It has a different rate at different times because it goes down steeper in some places than in other places during the day. At what time of day is the usage the greatest? Well, I'm going to suggest that at 7 o'clock, the usage is the greatest. Now, how do we know that? Well, since we aren't asked for a specific value at this point, we could say, well, the usage is going to be the greatest over time, since these are all the hour increments are the same, that we look at this and say, oh, okay, if it's using the greatest, it's going to go down the fastest. So here's a place where it goes down fast, and here's a place that goes down fast, but the slope of this line is not as much as it is here. If I was to draw the tangent line, I may say that the line comes down, oops, I missed it there at the whiteboard. Try it out a little bit closer. And over here, it looks kind of similar, but not quite as steep as over here. So this appears to be the time so far. We notice over here in the next day, it's also similar, but that's about the same time as it is over here. So it seems to be recurring at about 7 every day. Your sets, you can see that a little better. So it appears that at 7 a.m. our usage is the greatest because the amount of DUOS in the tanks goes down the fastest over this time. Now, if we take this particular part of it at 7 a.m., where the usage is the greatest, what is the rate of usage at 7 a.m.? Well, let's enlarge this so we can see a bit better, a little bit easier to try and find points when we enlarge the section here. So the usage of it is going to simply be the slope, the derivative. We notice here at point P, it crosses an x and a y exactly. And if we draw the tangent line in here, we notice, oh, well, here it also crosses an x and a y exactly. So if we find the slope from this point here up to P, then we are going to have what we need. So the change in y is, the y is 4,650 here. The y down here is 4,400. 4,650 minus 4,400 is 250. The change in y is 250. The change in x is here. It's not 1 because it's from 7 a.m. to 11 a.m., which is 4 hours. So the change is 250 over 4. And we notice, of course, that the slope is going down. So it's going to be negative. So the slope would be minus 250 over 4, which is minus 62.4. So, excuse me for that. So the usage rate is that we're using 62.5 cubic meters of Duyos over that time. And at all other times we're using it, but just not at that rate. It's the largest rate of usage. Now, it's negative, it means the tank is going down. We wouldn't say that the usage is minus 62.5 because that would mean that we're not using it 62.5. We're filling our tanks. The usage would simply be the positive value of this. The usage would say we're using 62.5 cubic meters of Duyos at 7 a.m. Now here's the homework. It's also on Moodle. I would suggest if you want to get started, some of these problems will take some time. If before class, if you could do section 1.1, the first 1 through 25, the odds here, that would be a good start to come to class with. If you have questions, we can go over it, and then in class we'll work on the rest of them. If you simply don't have time and want to get started, of course that's your choice. But then remember, with this kind of thing, an hour of class may not be enough time to get your homework done, so you may want to do something in advance. So again, this is on Moodle, and we'll see you in class next time.